Marie buys a new car for almost $25,000. Oh my goodness. That's at least like a 2020 Toyota Prius hybrid. Very nice. Sadly, when you buy a new car, the moment you drive it out of the parking lot, it loses like 5% of its value. But this is saying that, all right, each year it's going to lose 12% of its value. So it depreciates, right? The value depreciates. We're given a model for this, the value of the car, right? It's an exponential model. So the P for value, interesting, equals A times R for rate of depreciation, all to the power of T, number of years, right? Time. So exponential function. Our input would be time, and our output would be how much the car's worth, right? The value of the car. And the question we're asked is, right, how long will it take for the value to halve? So its initial value is 24,990. So we could half that, right? And then put that in for P to work out the time it would take to get to half of that value. But I'm a bit ahead of ourselves here. Let's first work out A and R in this formula here. So if you are not too familiar with exponential formulas, they are very similar, which is great. But if you haven't seen one, it'll be hard. Let's work out the value for A first. So A is like the initial condition, like the initial value. So if Marie buys a new car, we assign that at time equals 0, right? So the value of the car at time equals 0. And that's a point, right? We're essentially modeling, we have a function, it's got a starting value, and it depreciates over time. So we can use that point in our function to solve for A. So when P is 24,990, A, we don't know what it is. R, we still don't know what that is yet. T is 0, right? It's the initial time. R to the power of 0 is just 1. So we're left with A is equal to 24,990. All right, so that's finding A. So we've already updated our model to 24,990 times R to the power of T. Right, again, A just being that initial value, that initial condition. Now to get R, I call it the rate of depreciation, or like the rate of change, and it decreases by 12% each year. Okay, so after 1 year, what will we multiply 24,990 by in order to decrease it by 12%? Right, will we times it by something more than 1 or less than 1? Hopefully you're thinking less than 1. Yeah, and how much less than 1? Instead of timesing it by 100%, we times it by 100% minus 12%, right? Because it's decreasing by 12%. And that's 88%, or as a decimal, 0.88. So each year we multiply it by 0.88 to decrease the value by 12%. So just in here, we're going to replace R with 0.88. Right? So the question gave us that it decreases by 12%. We converted that to 0.88 because that's the thing we're multiplying by each year. So it's slightly different. Okay, so now we have a fully characterized model, right? And what I mean by that is the only thing that's unknown is the input and the output, right? Depends which way you go, right? But P and T. And now we can answer the question. So how long will it take for the value of the car to halve? So firstly, let's half the initial value. So 24990 divided by 2, 12495. 12495. So that's half the value. Everything else stays the same. Right, because that's our model. And we're looking for t. So here we have one equation, one unknown. That's good news, we can solve. I'll show you how to solve it using logs, which is the preferred algebraic method, but I'll also show you how you can solve it using your calculator. Let's solve this using logs first. We can divide both sides by 24,990 to get that 24,990 equals 0.88 all to the power of t. All right, and what on the left hand side, that should equal 0.5, right? Because 12,495 was half of 24,990. You can always check on our calculator. All right, and now to solve an exponential equation like this, we can take the log of both sides. So log of 0.5 equals log of 0.88 to the power of t. And then using the log law, which takes the power of the argument of the log. So the argument of the log just meaning what's inside the log. So we take the power and bring it out the front to multiply by the log. So that becomes log of 0.5 equals t times log 0.88. And now to solve for t, we can divide both sides by log of 0.88. So log 0.05 divided by log 0.88 will equal t. So t is equal to, now again, log of 0.5 and log of 0.88 are just numbers. So log 0.5. So log 0.5 is negative 0.3. We divide that by log of 0.88 to give us 5.422. 422 years. And that's to halve in value. All right, so just to recap that so far, we have an exponential decay problem, and we had to work out the model. So they gave us a hint, right? They gave us the general form of the model, but we worked out A, which was just the initial value. We worked out R, which was 0.88, which is 1 minus 0.12, because it decreases by 12% each year. So we then had our model, not there, right here. So that was a key step. Then we were looking for the time it takes for the value to halve. So we substituted in half of the value, and we then went on our way to solve for t. Right, in this case we used, we converted it to a log equation to then solve for t. Just a side note, if you want to solve this on your calculator, you can. However, it's not 100% always correct, so just be mindful of that. It depends on the problem, but good way to check anyway. So menu, go to equate for equation, F3 for equation solver. Now we input our equation, so that will be this one right here, right? So 12495 equals, so that's shift dot near the bottom there, equals 24990 times 0.88 to the power, so we don't have t, well we do, but it's just easier to use this variable button here, x, underneath alpha. So we've input the equation. Now this little window here is saying it's going to start searching for the equation from 0, and it's going to search between like -9 quintillion billion and +9 quintillion billion, whatever these numbers are, really big and small. But we just hit F6, solve. Alright, and so that's saying x equals 5.422, which is what we got using our log equation as well. So, save the marker some time, tick.